In this video, I will consider one more problem under t-test. In the t-test, we will calculate testing of hypothesis for difference of two population mean in this problem. So we will consider two sample. Using those two sample, I will calculate mean and I will show you finally how to take a decision using difference of two population mean and formulation of hypothesis for this kind of situation. Then without delay, let us consider some of the assumption that are attached to two sample t-test. So normally whatever the statistics you apply in parametric test, as I told you, it must be normally distributed. Even in t-test also it is the same case. In two sample t-test also the population must be normally distributed. It applies to the both population that are considering to the problem. So one more assumption of two sample t-test is, and the sample you collect and their observation both must be independent to each other. For example, in the problem ahead I am going to consider we have two types of diet foods, that's diet A and diet B. In this two types of diet foods, the relation between the diet food A and B, there is no relation. So these diet food A and B must be independent. There must not be any relation established between these two samples. That is what I am saying here. Samples and their observation both are independent to each other. If the sample are dependent, for that we will calculate one more t-test called paired t-test. But in this, in the two sample t-test, the two sample you are going to consider must be independent to each other. And one very important assumption along with the above two said assumption is that in two sample t-test, both variances, both population variances are unknown. Also unknown, and it must be equal. So population variance of population 1 and population 2 must be unknown and must be equal. It will come to know when I calculate the population variance for this. Then let us consider a problem for this. Here in this problem, we have random sample of 10 pigs fed by diet A, and the gain in weights in certain period were recorded and are given in this problem. So in this problem, 10 pigs are fed by diet A food, and gained by the diet A food during a particular period is recorded and given to us. And in another sample of 10 pigs fed by diet B, also the gains in weights in the same period, the period relating to diet A food, are recorded and given to us. So here very simple, there is a diet A and diet B food. There are two types of diet foods, so A and B, and these diet foods are given to 10 pigs by taking a random sample for a 10 pigs, and their gain in weights recorded for a particular period and given to us. Now what we want to do is, assuming that a gain in weights due to both foods follows normal distribution. These samples are collected randomly and these samples are normally distributed with equal variances. So now we want to test whether diets A and diet B differ significantly regarding their effect on increase in weight at 5% level of significance. Now what we want to do is, we have diet A and B foods. We want to test whether diets A and B differ significantly regarding the weight, increasing weight, and we have to test this hypothesis at 5% level of significance. So here we have two population sample. One is diet A food and one more is diet B food, and their weight gain in weight are given below for a particular period. Now our task is to test whether the gain in weights differ significantly. So firstly, let us formulate a hypothesis for this. Here we can test diets A and B differ significantly regarding their effects on increasing in weight of 10 pigs. So we can assume mu1 as diet A food, mu2 as diet B food. And we want to do is test whether diets A and B differ significantly. Since we want to test diet A and B differ significantly, our claim would be mu1 not equal to mu2. In the problem itself, they are asking us whether diets A and B differ significantly. So our claim is yes, it differs. As I told you, diet A food denoted by mu1, diet B food be denoted by mu2. So our claim would be, what we want to claim is diet A and B food differ significantly. So and complement diet A and B, which means mu1 equals to mu2. And which is a complement indicates that gain in weights of pigs from diets A and B foods are same. So here, since complement contains equality sign, we will take null hypothesis as complement, that is a mu1 equal to mu2. So we can state this as there is no significant difference between diet A and B food, which means diet A and B food do not differ. And our alternative hypothesis would be claim. So our claim is mu1 not equal to mu2, which means there is a significant difference, which means diet A and diet B food differs. So by this way we formulate a null and alternative hypothesis. Very importantly, we want to test whether diets A and B differs, food differs. So our claim is mu1 not equal to mu2, which means it differs, and complement is mu1 equal to mu2, and we have taken a complement as null hypothesis because it contains equality sign, and remaining thing as alternative hypothesis. So in the next slide I will show you the formula that we want to consider under two sample t-test. So for this problem, then the t-test of two population means can be obtained by this. So t is equal to x bar minus y bar. Since we are dealing with the two population, so we have to go calculate a mean of each population. So first sample, diet A food can be denoted by x bar, diet B food denoted by y bar, and in the denominator SP means population's standard deviation. As I told you in the assumption only, that I indicated in the third assumption, that both population standard deviation are unknown and but equal. So we want to make it equal. That's why sample standard deviation, we want to make a sample standard deviation of both population as equal. So we are considering SP, and in the t-test population, we are unknown about the population standard deviation, and here in the root 1 by n1 plus 1 by n2. n1 is a population 1, n2 is a sample of population 2. So it is very clear, since we are having two population, we have to calculate mean of each population and standard deviation of sample of both population. It must be equal, so we are going to calculate SP. In the problem, we know that n1 and n1 is a sample size of population 1 and n2 is a sample size of population 2, but whereas we don't know x bar, y bar and SP. One thing we should keep in our mind, unless we calculate, unless we know the x bar, y bar and SP, we cannot apply anything to this two population t test. So firstly, what we want to do is we want to calculate, we want to find out x bar, y bar and SP. So the formula we consider to calculate x bar, y bar and SP is that, so to calculate x bar, it is very simple. X bar can be obtained as A means assumed mean, A plus 1 by n1. So as I told you, x bar y is a population 1, that is the mean of diet A food. So diet A food is I will consider as a n1, that's a sample 1, and the things obtained in the x bar that is from the population 1 is D, that's a deviation taken from the sample value to assumed mean. So D1, I will consider D1 here. So the formula for calculating x bar is x bar equals to assumed mean plus 1 by n1 summation D1. We have to take sum of the D1, deviation 1. So the same formula we will consider for y bar also. Here I have denoted y bar as a mean of second population, and B is a assumed mean of second population, and since we are calculating mean for second population, I will consider sample size of second population. So n2 is a second population, and here D2 summation of D2, since we are dealing with population 2, sample of population 2, so I will take deviation of second population. So after calculating x bar, y bar, then we can calculate SP also. To calculate SP, you need to follow this formula. Actually, this is very simple formula that you need to understand it. So I'm going to calculate a square p firstly, then I will take root of it, then it will considered as standard deviation p. Firstly, I will consider sample variance. So to calculate sample variance, it is common that 1 by n1 plus n2 minus 2. So n1 is a sample size 1, population sample size first, and plus n2 is a population sample size, second population sample size, minus 2. Since we are considering 2 population, I will consider 1 population, 2 population. So I will subtract n1 plus n2 by 2. So this is a way you will obtain the degree of freedom also. And moving further within the bracket, here very simple, summation d1 square minus summation d1 whole square divided by n1. And here same formula, the formula we calculated here, but we have to consider the things for second population. That's a summation d1 square, here summation d2 square, here summation d1 whole square, here summation d2 whole square, here n1, here n2. Actually this is a very simple formula, but it looks so long. Need not to worry about this. This is a simple formula. Whatever you consider here, just you need to change the values for second population, and all the values, in the sense all the symbols remain same. Then what we want to do is, if you want to apply to this formula, we want to calculate x bar, we want to calculate y bar, we want to calculate SP, that's a standard deviation of sample. Then firstly, let us consider the sample values that are given in the problem. So after considering, we can calculate x bar, y bar, and variance of sample size also. So before we calculate x bar, y bar or SP, you can see in the formula for SP, we need d1, we need d1 square, we need d2, and we need also d2 square. So for that I have to take deviation from the sample value. These are the sample values given in the formula. So x is a first diet A food pig's weight gain. The recorded values are listed here. So here 10 samples are there, 10 values are there, sample values are there. So to take deviation 1 is a sample size, population sample size 1, population 1. So I have considered d1. To take deviation is equal to x minus a. X is a sample value, a is a assumed mean, and here I have taken assumed mean as 12. I have taken assumed mean as 12 since it is a reasonably okay to take assumed mean. Somewhere it will come around or aside or beside of 12. So I have taken assumed mean as 12. So I will take deviation in the d1. I will take deviation for all the 10 values. Firstly 12 minus 12 0. Second 8 minus 12 minus 4. And the third value 14 minus 12 2, positive 2. 16 12 4. 13 12 1, 12 minus 12 0, 8 minus 12 minus 4, 14 minus 12 2, and 10 minus 12 2 minus 2, 9 minus 12 minus 3. And when I taken the sum of the d1, that's a deviation 1, I will get minus 4 value. So in the next column we have d1 square. The values I have taken deviation, I will make it a square. So the squared values here 0 into 0 0, minus 4 into minus 4, and 16 2 into 2 4, 4 into 4 16, 1 into 1 1 only, and respectively all the values made a square of the same value. So if you take d1 square is 70. Whatever I calculate for x, that's a sample size, population sample size 1, that's a diet A food. The same thing I will calculate for diet B food also. So diet B food I have denoted as y, and I have a sample values of y here. We have 10 sample for diet B food also. So to take deviation d2, I am considering population 2. So d2 is equal to y is assumed mean, y is a sample values of population 2, b is the assumed mean of population 2. So here I have taken b, which means assumed mean of sample population 2, b as 16, which is a reasonably okay. As I said, you side or beside we will get the same value in the mean of. So here also what I have done is, I have subtracted sample values from the assumed mean. Sample value, first sample value is 14 minus 16 minus 2, 13 minus 16 minus 3, 12 minus 14 is 16 minus 4, 15 minus 16 minus 1, and so on. All the values are obtained as follows, as I given an example like this. And in the third column of diet B, we have made square root of the deviation 2. So minus 2 into minus 2 plus into minus plus, so 4 minus 3 into minus 3 16, 4 minus 4 into 4 16, and as follows. The values obtained as follows. We have made a d2 square, and in the diet B we have d2 as minus 5, we have d2 square as 65. So far we have obtained d1, d2 square, d1 square, and d2 square also. So that obtained values I have listed here. These are the very essential for the formula, to apply formula. That's why I have shown you in separately. So assumed mean A is a population 1 assumed mean 12, B is a population 2 assumed mean, D1 is a population 1 deviation, so minus 4, D1 square it is 70, population 1 deviation square, and D2 is minus 5, here it is minus 5, population 2 deviation, and D2 square here it is population 2 deviation square, and N1 is a sample size of population 1. We have 10 sample as I told you, so N1 is 10 and N2 is also same thing, 10. Now after obtaining all these values, we can go and we can move on to calculate X bar, Y bar and SP. So then let us look into that. The same values I have pasted here to make a difference, to replace with the formula. So here A is assumed mean is 12, 1 same, and N1 is 10, and D1 here we have minus 4. So then I have replaced all the values here. A1 12 and N1, here N1 is 10, and summation D1, sum of the D1 deviation 1 is minus 4. So firstly I will divide 1 by 10. I will take this part first, then I will add to this assumed mean. 1 by 10, 0.1 into minus 4, and after making that I will take a minus value. So minus value, that's 0.4. So 12 plus into minus 12 minus 0.4, I will get X bar is 12.6. Mean sample mean of first population is 11.6. So this is after applying to the formula. I have simplified that formula. So then as we calculate to the first sample mean, we can also calculate to the second sample. The formula as I shown you, Y bar is equal to B is assumed mean for second population, 1 by N2 and D summation D2. So here B is, as I told you, 16 and N2 is 10, D2 here, D2 is minus 5. So then I have replaced the formula and I have also obtained the values. As I told you, 1 by 10 into minus 5, we will get 0.5, 16 plus into minus 16 minus 0.5, 15.5. So then we have obtained X bar and Y bar. Then we have to calculate SP. Here in the right side I have calculated SP also. As I told you, I have copied the formula. So formula is this, and relevant information we have here to apply to the formula. Here N1 is 10 plus N2 is 12. Since we are considering two population, I will subtract N1 plus N2 by 2. So in the square bracket summation D1 square, very importantly you should not confuse with D1 and D1 square, because here D1 square here, because and here summation D1 whole square is different than square. So I will consider D1 square is minus 4, and here summation D1 is minus 4 here, and summation D1 square is 70, and N1 is 10. Here summation D2 square is 65, summation D1 whole square is minus 5, and N2 is 10. So the thing I have replaced with the values here is N1 10, N2 10, minus 2, summation d1 square 70, here it is 70, and summation d1 whole square, sorry, it is a square, the summation d1 is minus 4 whole square divided by n is at 10. So summation d2 square is here, it is 65, and summation d2 whole square 5 minus 5 whole square divided by 10. Now in the next step I will simplify this formula. So when I simplify this, 10 plus 10, 20 minus 2, so 1 by 18, and 17 remains as it is. Here minus 4 into minus 4, 16, then 16 by 10, 1.6. Since in the numerator here it is a minus, so here it is a minus, but minus into minus plus, so 16 plus 16 by 10, we have 1.6. So 70 minus 1.6. In the next step I will simplify this too. Here also same thing, 20 minus 5 into minus 5 plus 25, 25 by 10, 2.5. So in the next step you can see 1 by 18, 70 minus 1.6 plus 65 minus 2.6. When I simplify this value also, I will get next step. When I say divide 1 by 18, I will get 0.055555. So and 70 minus 1.6, that is 68.4 plus 65 minus 2.5, 62.5. So when I add these two values, I will get 130.9. So in the next step I have to multiply with 0.05555 into 130.9. When I multiplied that, I will get 7.29. So then we obtained sample variance of both population, and here you can see ultimately the both population sample variance is same, equal. We have seen in the assumption both population variance must be equal. So here it is equal. Whereas to apply to the formula, we need SP, that's a sample standard deviation. So if you take root of it, you will get SP also. So I have put this value 7.27 into the root. So when I take a root of 7.27, I will get SP, that's a standard deviation of both population is 2. So by calculating we obtained SP standard deviation of the sample. Also we obtained y x bar 11.6 and y bar 15.5. With these three values we can apply to the t-test for difference of two population mean. So then let us consider the formula for t-test difference of two population mean. Here we have x bar, we want x bar, we want y bar, we also want SP that we have calculated already, and in the root 1 by n1 is a population first population sample numbers, the sample size, n2 is a second population sample size. Here we have all the related data. I will replace these values to the formula. Here I will consider x bar as a 11.6, y bar as a 15.5, SP as a 2.70, and n1 n2 as 10. So here in the right side we have replaced all the values. 11.6 minus 15.5, 2.70, 1 by 10 in the root. So I will simplify this formula. So 11.6 minus 15.5 minus 3.90. So greater value having a negative sign, and in the denominator I will divide 1 by 10. I will get 0.10 plus 1 by 10, so 0.20 when I add these two value. So in the next step I will take root of 0.20 and I will divide the value obtained by root by 2.70. So the value is 1.215. Now I have to divide minus 3.90 by 1.21. So then finally I obtained by simplifying the values in the formula. So our tested statistics of t is minus 3.21. Now I have to obtain critical values from t table of t distribution. Then I have to compare with the t distribution with our t tested value with the critical value. Then I can take decision. Firstly I have to obtain critical values from the t table. So for that we are obtaining the table value of tested statistics. This is a two-tiered test since alternative hypothesis are two-tiered, and for that we are considering two populations. So n1 plus n2 minus 2. Since we are considering two population, we have to subtract n1 plus n2 by minus 2. If it is only one population, we n1 n minus 1 I can subtract, but here two population. In our example, n1 is a 10 sample, n2 is a 10 sample, 10 plus 10, 20, 20 minus 2, 18. 18 is a degree of freedom. We have to see 18 degree of freedom at 5% level of significance in the table. So before that, since it's a two-tiered test, I have to adjust alpha. The alpha I obtained, I have to adjust. So to make adjust plus or minus t, n1 plus n2 minus 2, comma alpha by 2. So n1 n2 20 minus 2 18, and alpha our alpha is 0.05. so when I divide alpha by 2, 0.025. why should I divide alpha by 2? Means we are going to look critical values of t table from the upper tail probability distribution of t, so which means one-tailed value. So for that I have to divide alpha by 2 so that I can consider my alpha to the one-tailed values. So the values we obtain from the table is plus or minus 2.101, which is a critical value for our 5% level of significance at 18 degree of freedom. I will also show you how to obtain these values from the t distribution t table. This is our t table, as I keep on saying you, upper tail probability. This upper tail probability. That is why we have divided alpha. That our alpha is 0.05 by 2. So adjusted alpha to our example is that when we divide 0.05 by 2, our adjusted alpha is 0.25. As I told you, our degree of freedom, also we have calculated degree of freedom in the last slide. So degree of freedom for this is 18. That's a 10 plus 10, 20 minus 2. Our degree of freedom is 18. So now we have to look a critical value for 18 degree of freedom at 0.025 level of significance. So this is a value, the corner value is a degree of freedom, critical value for our problem. So for this problem, critical value is 2.101. So by this way we also obtained a critical value. Also we have tested value. Now we have to compare critical value with the tested value so that we can derive at a conclusion. Since it is a two-tailed test, rejection reason falls in the both side of the sample distribution. So here, as I keep on saying you, this rejection reason, our alpha is 0.05, so which is divided by 2, 0.025 from the right side, 0.025 from the left side, and critical value just we obtained from the table, that is a plus 2.101 from the right side and minus 2.101 for the left side, and our non-rejection region is an unshaded area, and we want to know where is our test statistics and where is our critical value. So this at minus 2.101 is a critical value. Our tested value is minus 3.21, and here we can see which is a minus 3.21, which falls in the left side of the sample distribution. This red line is the minus 3.21, which clearly showing us which is the test statistics is falling in the rejection region of the sample distribution. And here our critical value ends at here, and in the both side ends at green shaded area. So we can arrive at decision, since calculated value of test statistics is minus 2.21 is less than the critical value of plus 2.101 or minus 2.101, because it is beyond the critical region, which means our test statistics t lies in the rejection region. Since it is lying in the rejection region, we reject the null hypothesis and support the alternative hypothesis at 5% level of significance. We support our claim. By this we can conclude that samples do not provide us sufficient evidence against the claim. So diets A and B differ significantly in terms of gain in weights of pigs. Thank you so much for watching. Please do subscribe to my Vision Academy YouTube channel. Thank you.